Oh, hello. It's from Danielle from NanoPattern. It's going to talk about different microLED architectures and color conversion. We're still on this similar topic. I see you're already ready, so you have the floor, Danielle. Thank you.
All right. Yeah, thanks very much for inviting me. And today we're going to talk about the efficiency resolution and gamut trade-offs of really comparing a quantum dot downconverted microLED architecture to a direct RGB architecture. And at NanoPattern, we are developing quantum dot downconverters for microLEDs, such as the ones that you see behind on the screen. Because of that, we wanted to convince ourselves that the quantum dot downconverted architecture could be competitive in performance with a direct RGB type of architecture. And so to do that, we have done an analysis, a literature survey of latest results of across the industry on the efficiency and properties of direct RGB architectures. And there's a few challenges that we see, especially for red microLEDs, as we advance microLED architecture and go to smaller and smaller pixel sizes. So the traditionally red microLEDs have been made from a different semiconductor material than red and green than the green and blue, and that is aluminum indium gallium phosphide. And when you use the aluminum indium gallium phosphide and try to combine with indium gallium nitride, the current at which you get the maximum efficiency is very, very different for those two semiconductor systems. And so this makes a very large current offset in between where you would like to drive the aluminum indium gallium phosphide, the red pixels, and the green and blue pixels. It makes drive electronics very challenging. Second issue is what happens as you reduce the die size of those pixels. And you see a strong drop in efficiency. And the reason for that is that the amount of area of the sidewall compared to the area of the center of the die increases. And so the distance between any carrier that gets excited in the center of the die and a potential trap on the surface of the edge of the LED, that distance shrinks. And so for any microLED, you will see a drop in efficiency as the pixel size gets smaller. But for the red aluminum indium gallium phosphide material, this is particularly severe, and that's because it has what's usually considered a good property, a large minority carrier diffusion length. But in this case, it's a challenge for that material. Some people have tried making red directly out of indium gallium nitride, and in fact, that does not show the strong size dependence. But unfortunately, that material is comparatively inefficient, as you can see with the X's and stars at the bottom of the graph on the right. And then, so finally, the most obvious challenge for direct RGB is that you are combining LEDs from three different semiconductor wafers: a blue wafer, a green wafer, and a red wafer, and that requires more mass transfer. So we think that quantum dot downconverted microLEDs can address all of these challenges. We can enable smaller die sizes, we can simplify the mass transfer, and we can make the drive current very uniform just by only driving blue LEDs. Uh, but the question is, can we make the performance of the quantum dot downconverted microLED competitive? So to do that, we took the numbers from that meta-analysis. We took the average best-in-class blue LED, and we compared with the uh, uh,